So in this video, we're going to pick up where we left off last time. Last time we talked about how the fractions of oil can be separated into useful different bits using the boiling point. Now we're going to talk about specific processing related to cars and combustion engines. Now, I want to be clear that the reactions that I'm going to discuss here will never be asked directly on a test. You don't need to memorize these, you don't need to know the name. But these are important processes for processing our hydrocarbons and meeting some of the needs in society. So I'm going to quickly go through it, but again, I would never ask you to come up with these reactions from nothing, but I might be able to use them if I was asking a question for you to if I gave you the reaction, I could say, so I would give you the balanced reaction. I could say, what is a possible product? And then give you a list of names. And can you match the molecular name to the structure? But I wouldn't ask you to give you the reactants and say, what are the products? Or what is this reaction specific to do? So this is more like context and deeper understanding sort of work in this. So catalytic cracking, essentially when we've got hydrocarbons, we do not make enough oil through fractional distillation to meet our needs for cars. So what they do is in catalytic cracking, they're going to take a large hydrocarbon and they're going to split it in half. So they heat it up and they'll make something like C8H18, and it's going to split and break into another molecule. So you would expect, because you've got 8 of these, that this will be like C9H, well, it's an alkane, so it's got to be H20. But if we look at this, the hydrogens don't work out here, right? So if I've got 36 hydrogens here, I'd have 38 hydrogens here. So that doesn't work. So what ends up being produced instead is you get carbon waste. So this is carbon waste, carbon solid waste, and then you get C8H18, and you get your 36 hydrogens, and you've got your 16 plus 1 carbons. So if I was writing it like this, obviously this is a dumb way to make it look like it was balanced. I would maybe write this, right? So that'd be catalytic cracking, where I can split a molecule into 2 different molecules. Now it doesn't exactly split in half. So the molecule could be C9H20. I'm going to still produce that carbon, and so I've got C7H16 is the other product. So it's one of the reasons we don't ask you to come up with these reactions from scratch. Is there are lots of possible products. But if I wanted to use this in a question, I could give it as context and say, now, which of these molecules is an isomer of this? Hydrocracking solves this waste carbon problem. It'd take C17H36, it'd add a hydrogen to it, and now I can get C9H20, and I can get C8H18, because now I've got enough hydrogens to complete it. So it produces a little bit of less waste carbon that's kind of useless, but I need to have a supply of hydrogen to be able to do that. So this is a way for us to increase the amount of gasoline that's produced. We take bigger molecules, split them into 2 smaller molecules that can both be used as gasoline in cars. Cars also have different grades of gasoline. So if you go and buy gas, there is like, the silver or bronze, silver, gold, or whatever. And on those different, usually it's 3 different levels of gasoline that you can buy. It's sort of like cheap, expensive, really expensive. The reason for that is that there's an octane number. And so they'll write that on. It'll be like 92 or 97 or something like that. The octane rating is related to what kind of engine is burning this fuel. So the fuel is going to need to be burned in a combustion engine, and it can't burn too quickly. So essentially what happens in a combustion engine is you have a piston that's going down, and at the same time you've got a piston that is going up, and they're in a chamber, and in that chamber you've got a an explosion in one chamber, and we do not have an explosion in the other chamber. And these two pistons are connected, and so if one goes up, the other goes down. So we want that explosion to be perfectly timed so that the one piston goes up, the other piston can go down. Well, if you have lower octane fuel, the explosion happens at lower pressure and lower temperature. In a high performance car, the explosion, because it's happening in such a high performance, high pressure heated engine, you get tons of power out of it by having a better, like a really finely tuned explosion. But low quality gasoline, or not low quality, but low octane number gasoline, will end up having the explosion happen at the wrong time. And you can literally break apart a high performance engine. So the way that they can improve octane is make it, or have a higher octane number, is to make it so that it's less likely that you get that explosion happening wrong. And the way they do that is by making more aromatic rings and more branched alkanes. So if I had C8H18, it could make a benzene ring through catalytic reforming that uses 6 of my carbons, and then an ethyl. So ethyl benzene could be produced, or perhaps you'd get dimethyl benzene, and you'd get 3 hydrogen gases. And this molecule is going to resist that exploding under higher pressure, like in a high performance car like a Porsche or something like that. So in a Porsche, you have to put in higher rated gasoline. My car, which is not a Porsche, does not require that. So I put in the cheaper gas because it's cheaper and it works fine in my car. Alkylation does a similar thing, but instead what alkylation does is it takes a straight chain. So if it was an octane, so I had 1, 2, 3, 4, whoop, didn't like that. 1, 2, 3, 4, 5, 6, 7, 8. That straight chain, if instead it had branches, this kind of molecule also resists combustion under higher pressure and higher temperature. And so having more of those two kinds of molecules, of having aromatic rings and branched chain alkanes, increases the octane number, and they can charge more money. So they can do that through the reactions like catalytic reforming and alkylation. You're again not responsible for knowing what the catalytic reforming reaction is or alkylation reaction, but if I gave that as context in a question, I would expect you to be able to name this, suggest an isomer for this, name this, tell me if they're isomers or not, which one should have a higher boiling point or a lower boiling point, right? And in this case, because this has got more branching, it's going to have a lower boiling point because its London dispersion force should be slightly smaller, even though they're both still C8H18.